Right, we are going to do about the refractive index. Unfortunately, Mr. Bolton is not here, so I have to do it instead. My name is Michael Kane. What you have to know is that the ratio of the velocities and the ratio of the wavelengths will give you the ratio of the refractive indices of the two different media. This number 1 is referring to the first media. This number 2 is referring to the second media. So this will give us an equation. So the light comes in from the air, from the first media, like that. Then it gets refracted, which means it bends towards the normal into the second media, like that. Now we can write that as the ratio of the velocities is the same as the ratio of the wavelengths, which will be the refractive index of the second medium, and it's also the ratio of the sines of the angles. This is basically Snell's law. However, n over 1 is a bit of a special case because 1 is referring to the vacuum or to the air, because this is the actual refractive index of air. So sometimes it's referred to as the refractive index of the first medium. So you can write it like that, n2 over n1. n2 is the refractive index of the second medium. Refractive index of the first medium is n1. Here we have the same thing again, but this time we're going from glass to air, not air to glass. So the light comes in on the glass side and then gets refracted away from the normal on the air side, like that. So the angle of refraction is actually greater than the angle of incidence. But some light, as you notice, gets internally reflected. So some refracted light is refracted away from the normal and some is internally reflected inside the glass. Doesn't come out, it stays in the glass. But if you notice, we've got medium 1 and medium 2. Medium 1, medium 2. Medium 2 for the refractive index of the second medium compared to the 1. Now this time we've swapped it round. The first medium is not air, it's glass. So where we have 1, we're going to change that to G for glass. And when we have 2, we're going to change that to A for air. So we'll change all those round. Notice this is glass divided by air. Glass divided by air. This is refractive index of air divided. This is refractive index of air divided by glass, and this is a sine of the angle of refraction in the glass compared to that of the air. Notice that the Vg in glass is actually slower than the velocity in air. So this will be less than 1, this will be less than 1, this will be less than 1 because you are dividing by a larger number, which is the refractive index of the second medium. So another example is that this is coming in at a very wide angle, but what happens is that it all gets refracted at 90 degrees. So what really happens is that this angle, which is 90 degrees, what happens to the light? It doesn't actually get transmitted, it stays pretty much where it is, or rather gets reflected internally. So we call this total internal reflection, and not a lot of people know that. This angle, which is the smallest angle at which you get total internal reflection, is called the critical angle. Now here's the equation that we had before. Na, we know, is the refractive index of A, which is the refractive index of the air, which we know is equal to 1. Theta A is basically going to be the refractive index, the angle of refraction in the air, which is 90. So we can write it like this: 1 over Ng, which is the refractive index of the first medium, which is the glass, is equal to the angle of incidence in the glass compared to the sine of 90 degrees. We can simplify that because we know what sine of 90 degrees is, and it is equal to 1. And not a lot of people know that. So to summarise, when it comes in on the critical angle, it's all going to be totally internally reflected. And this you have to know. And not a lot of people know this.